March 2, 1979, Sabra, California. A scientist was sitting at his desk. In his hand was a paper he had just published in the journal Science. His name was Stan Peele, and in that paper, Peele had made a prediction that the entire scientific community at the time found absurd. He wrote that there should be widespread volcanic activity on the surface of Io, one of Jupiter's small moons, a moon comparable to our own moon, a moon about which almost nothing was known at the time. Peele didn't have a single close-up picture of that moon. He had no direct observations. Yet, relying solely on mathematics and the gravitational calculations of Jupiter and the other moons, he claimed that volcanoes must be erupting there. It was a massive claim and a very dangerous one, because if he turned out to be wrong, his career could be over. But there was one thing in his favor. Exactly 3 days later, on March 5, 1979, the Voyager 1 spacecraft was due to pass near Jupiter, and Voyager's cameras were set to send back the first detailed images of Io. That meant in just 3 days, the world would know whether Stan Peele's prediction was correct, or if he would forever be remembered as the man who made a crazy prediction. 3 days later, Voyager passed Jupiter. It took thousands of pictures of Io, but there was a problem. Nothing extraordinary appeared in those photos, just a strange, colorful surface that left scientists confused. No active volcanoes were visible, no lava flows, no plumes. For an entire week, Peele's prediction remained unconfirmed. For a week, scientists studied those photos and found nothing. And then, on the morning of March 9, 1979, a navigation engineer at JPL was sitting at her desk. Her name was Linda Morabito, a brilliant, though not yet widely known, 25-year-old scientist. Her job was to confirm the position of the Voyager spacecraft. It was a very ordinary task, far removed from scientific glory. The photos Voyager was sending of Io weren't the kind of scientific photos that make headlines. They were navigation photos. In other words, the purpose of those photos was simply to verify Io's position so that Voyager's course remained correct. A new photo arrived on Linda's desk. She loaded it into the computer. She brightened the image and increased the contrast so that the background stars would be clearly visible. This was her routine. To do this with every photo to ensure navigation accuracy. But something was unusual about this photo. On the edge of Io, a crescent-shaped cloud was visible in space, extending from its surface. A very faint cloud, but clearly a shape that shouldn't have been there. At first, Linda thought it was a camera artifact, a glitch, or perhaps another moon that had drifted into view. One by one, she tested those possibilities. She ruled each one out, and as she did, her breathing quickened because only one explanation remained. That cloud was coming from Io itself. It was from the moon's atmosphere, and it was so large, 270 kilometers high, that it could be nothing other than a volcanic eruption. Linda had discovered what the world had been missing for a week. Voyager had captured that photo on March 5th. For 4 whole days it sat in the data right before everyone's eyes. And no one noticed because the photo was for navigation, not for science. And no one expected a navigation photo to reveal a discovery that would change our understanding of the entire solar system. Stan Peele's prediction. The prediction of that determined scientist that was supposed to be validated in just 3 days was finally validated, 4 days late, and through a navigation engineer who wasn't even part of the race for scientific recognition. On March 12, 1979, Linda's discovery was announced to the world, and on that day, our understanding of the solar system changed forever, because until then, we believed Earth was the only place where volcanoes erupted. After that day, we learned there was another place, and that place is far more violent than Earth, far more extreme, far more alive. This is the story of a moon caught in an eternal battle of fire and ice. A world where scientists claimed for 45 years that there is a global magma ocean, and which in 2024 quietly proved them all wrong. A place where mountains rise as if they are bursting out from deep within the ground. This is the story of Io. To understand the story of Io, we first need to understand Jupiter. the largest planet in our solar system, so massive that all the other planets seem like dwarfs beside it. And around this giant, approximately 100 officially recognized moons orbit. That number continues to grow as we discover new, smaller moons. Among all of these moons, 4 are especially remarkable. 4 that Galileo Galilei first observed in 1610 through one of his small telescopes. Since then, they have been known as the Galilean moons. Their names are, from the outermost inward, Callisto, then Ganymede, then Europa, and finally the innermost, Io. Callisto and Ganymede are solid worlds made of ice and rock, their surfaces covered in craters. They are quiet and ancient, with very little having changed on them for countless ages. Then there is Europa, a thin, smooth shell of ice with a vast liquid water ocean hidden beneath it. Alien life may exist on Europa. It remains one of the most promising places in our solar system for finding extraterrestrial life. And then there is the innermost moon, Io, orbiting about 421,700 kilometers from Jupiter. That distance is only slightly greater than the distance between Earth and our own moon. In terms of size, Io is almost as large as our moon, just a little bigger and a little heavier. But there is one thing that makes Io different from all the others. Io is the densest moon in our solar system. All of the other large moons are mixtures of ice and rock. But Io is made almost entirely of rock and metal. It is so dry, so completely devoid of water, that scientists believe no major body in our solar system contains less water than Io. Even compared with Europa, a moon that hides an immense ocean beneath its icy surface, Io is far more barren. But the real story is not hidden deep inside Io. The real story unfolds across its surface. There are currently around 400 active volcanoes scattered across Io. At any given moment, somewhere on the moon, an eruption is taking place. Somewhere lava is flowing across the landscape. Somewhere, a towering cloud of sulfur is rising into space. Somewhere the ground is slowly sinking. Somewhere else, a new mountain is lifting itself toward the sky. This is the only place in the entire solar system, besides Earth, where we know volcanoes erupt on a regular basis. And it is not simply active, it is extraordinarily active. It is the most volcanically active world in our solar system. The question is, how? Io is so far from the sun that almost none of the sun's warmth reaches it. Away from its volcanic regions, surface temperatures fall to around negative 130 degrees Celsius. Cold enough that almost everything familiar on Earth would freeze almost instantly. So where does all of this fire come from inside such a frozen world? Where does the magma come from? Where does the energy originate that keeps roughly 400 volcanoes continuously active? The answer lies in gravity. But not just gravity alone. A very specific kind of gravity. Io is trapped in an extraordinarily dangerous position. On one side is Jupiter, the most massive planet in our solar system. Its gravitational pull is so powerful that if Io orbited even a little closer, it could eventually be torn apart. On the other side are the other 3 Galilean moons. They are also massive worlds, and their own gravity constantly tugs on Io in different directions. As a result, Io is caught in an endless gravitational tug-of-war. Jupiter pulls from one side, while the other moons pull from another. Because of this constant struggle, Io's orbit is not a perfect circle. Instead, it is slightly oval, meaning that sometimes Io moves a little closer to Jupiter, and sometimes a little farther away. This entire cycle repeats every 1.7 days. What does that mean? It means Io is constantly changing shape. As it moves closer to Jupiter, the planet's immense gravity stretches the moon. As Io moves farther away, that pull weakens, and the moon relaxes back toward its original shape. Then it is pulled again, then released again. Over and over, every 1.5 days, for billions of years. The result is extraordinary. Here on Earth, the moon's gravity raises ocean tides by an average of about 0.5 meter. But on Io, there are no oceans creating tides. Instead, the tides occur in solid rock. Jupiter's gravity lifts Io's rocky surface by as much as 100 meters every 1.5 days. The solid crust of an entire moon rises as high as a 30-story building, then slowly settles back down, only to rise again without ever stopping. This endless stretching and squeezing works like a giant pump. It generates tremendous friction deep inside Io. That friction produces heat, invisible heat that reaches all the way toward the moon's interior, melting solid rock into magma. Scientists call this process tidal heating. And this was the very process that Stan Peele predicted back in 1979. In other words, Io is a world where volcanoes are powered not by the sun, but by gravity. A place where the source of fire is not sunlight, but an endless gravitational tug-of-war. But Io's volcanoes are not like the volcanoes we know on Earth. When we think of volcanoes, we usually imagine towering mountains with lava and ash erupting from their peaks. Mount Vesuvius, Krakatoa, and Mount Etna all formed where Earth's tectonic plates meet. As those plates collide, molten rock rises from deep below, and over time, mountains are built. But Io has no tectonic plates, so its volcanoes do not create towering mountains. Instead, they erupt directly through enormous cracks in the surface. The eruptions are sudden, direct, and incredibly violent. Among all of Io's volcanoes, one stands above the rest. It is the most powerful active volcano anywhere in our solar system. Its name is Loki Patera. Nearly 200 kilometers across, it is a remarkable type of volcanic feature known as a lava lake. Imagine an enormous depression filled not with water, but with a vast lake of molten rock. Yet there is something even more extraordinary about Loki. It is a volcano with a pattern. How predictable is it? Here on Earth, we still cannot accurately predict the exact day when most volcanoes will erupt. But Loki Patera, on a distant moon, hundreds of millions of miles away, once erupted every 40 days, again and again, following an almost perfect schedule. Throughout the 1990s, scientists carefully monitored it, and each eruption occurred almost exactly when expected. Then, in 2001, something changed. Loki's cycle suddenly stopped. It remained quiet for an entire 12 years. Scientists were puzzled. Some even wondered whether the volcano had become permanently inactive. But in 2013, Loki came back to life with a new rhythm. Now it erupts roughly every 475 days, a little faster, a slightly different pattern, yet still remarkably regular. To explain this strange behavior, scientists proposed an astonishing idea. Loki is a lake, but instead of water, it is filled with molten rock. A thin crust slowly cools and forms across the surface of the lake, becoming solid over time. Meanwhile, fresh molten rock continues rising from below. Eventually, that cooled crust becomes so heavy that it can no longer float. It suddenly sinks into the molten rock beneath it, exposing fresh, glowing lava at the surface. Then, a new crust begins to form. It cools. It grows heavier. It sinks again. The cycle repeats without end. This means Loki Patera effectively swallows its own surface every 475 days. In the process, it releases the strongest thermal signal of any volcano in the entire solar system, a signal so powerful that astronomers can detect it from Earth using telescopes. But Loki is not alone. There is another volcano on Io named Pele, and another called Tvashtar. These volcanoes produce enormous plumes, the same kind of towering eruptions that Linda Morabito first identified in 1979. In 2007, Tvashtar produced a plume reaching about 330 kilometers into space. By comparison, the Kármán line, commonly used as the boundary of space above Earth, lies just 100 kilometers above our planet. That means Tvashtar's eruption reached more than 3 times that height. As sulfur and sulfur dioxide from these giant plumes eventually settled back onto the surface, they spread across hundreds of kilometers, forming enormous red rings around the volcanoes. Many of these colorful rings can still be seen across Io today. Each one marks the activity of a different volcano. Each one tells its own story. The sulfur released during these eruptions transforms Io into what almost looks like a living painting. The bright yellow regions are places where sulfur has cooled and crystallized into solid deposits. The white and bluish areas are frozen sulfur dioxide found in the coldest, permanently shaded regions of the Moon. The green areas are rich in sulfur monoxide, created through interactions with Jupiter's intense radiation environment. And the deep red regions mark places where volcanic eruptions have happened recently and where the sulfur remains extremely hot. In other words, Io's surface is a constantly changing work of art. Every color represents a different physical process. Every patch tells a different story. Yellow speaks of crystallized sulfur. White reveals the coldest shadows. Green records the effects of radiation. Red marks the heat of fresh volcanic activity. And unlike a painting hanging on a wall, this one never stops changing. Every day, every week, every month, a canvas that never truly dries. That naturally leads to a fascinating question. If Io has so many volcanoes, and if it continuously produces such enormous amounts of magma, what does its interior actually look like? For 45 years, scientists believed the answer was a global ocean of magma hidden beneath a solid outer crust. Even Stan Peel's original work in 1979 pointed toward that idea. Later observations from the Galileo spacecraft appeared to support it as well. Scientific papers, textbooks, documentaries, and computer simulations all portrayed Io as a moon containing a worldwide magma ocean beneath its surface. Then, in 2024, NASA's Juno spacecraft returned data that completely overturned that long-standing picture. Juno performed 2 extremely close flybys of Io, one in December 2023 and another in February 2024. On both occasions, it passed only about 15,500 kilometers above the Moon's surface. During those encounters, Juno collected one crucial measurement. It measured exactly how much Io is stretched by Jupiter's immense gravitational pull. That single measurement would reveal the true nature of Io's hidden interior. The logic was surprisingly simple. If there were a global magma ocean inside Io, then the entire Moon would deform easily under Jupiter's immense gravitational pull, almost like a water balloon. It would be highly flexible. But if Io's interior were mostly solid, it would remain much more rigid and resist that stretching. Juno's measurements clearly pointed to the second possibility. Io was rigid. It was not flexing nearly as much as a global magma ocean would require. That meant there is no worldwide magma ocean hidden beneath Io's surface. For 45 years, the scientific community had assumed exactly the opposite. For 45 years, Io had been portrayed as a moon with a global ocean of molten rock. For 45 years, textbooks, scientific papers, documentaries, and computer simulations all relied on that picture. Then, one set of measurements changed everything. So where do Io's nearly 400 volcanoes get their magma? The answer is even more remarkable. Instead of existing in one enormous global ocean, the magma inside Io appears to be trapped in hundreds of separate reservoirs. Independent pockets of molten rock scattered throughout the Moon's interior. Each one forms where tidal heating is strongest. Every reservoir feeds its own volcano, almost like an individual engine. That means Io is not powered by one enormous volcanic system, but by hundreds of separate volcanic engines. Each operates from its own isolated magma chamber. Each follows its own rhythm. Each volcano has its own unique behavior. Some remain quiet for years before erupting again. Others are restless, constantly changing and releasing fresh lava. It is almost as though Io does not beat with one heart, but with hundreds of them. And this discovery also helps explain another of Io's greatest mysteries. Its mountains. Mountains? Io has no tectonic plates. And as we've already learned, its volcanoes do not build mountains the way volcanoes do on Earth. So where did those mountains come from? That question has puzzled scientists for decades. Dozens of enormous mountains rise from Io's surface, tall, sharp, completely isolated. The tallest reaches nearly 18 kilometers above the surrounding plains. That's almost twice the height of Mount Everest, nearly twice the height of Earth's tallest mountain, standing on a moon only slightly larger than our own. But what makes these mountains truly extraordinary is that they stand alone. On Earth, Mountains almost always occur in long ranges: the Himalayas, the Rockies, the Alps. They form chains because they are created by the movement and collision of tectonic plates. One mountain follows another across hundreds or even thousands of miles. Io's mountains are nothing like that. Each one stands by itself. A single towering peak rises abruptly from an otherwise flat landscape. Nothing surrounds it. Just an immense plain, interrupted by an 18-kilometer wall of rock reaching toward the sky. By Earth standards, that simply should not happen. Here, mountains take millions of years to form. Yet Io's mountains appear almost as though they burst out of the ground all at once, as if something deep inside the moon suddenly pushed upward through the surface. It's a bit like that unforgettable scene in the movie Alien, where something hidden inside suddenly bursts outward. Io's mountains give that same impression. They seem to erupt from the landscape without warning. No mountain ranges, no obvious pattern. Just solitary giants appearing where there was once only flat ground. Scientists have proposed an explanation that is just as fascinating. When one of Io's volcanoes erupts, the ground above it can collapse, creating an enormous depression. That depression gradually fills with molten rock, forming a vast lava lake. But as that section of the crust sinks, the surrounding crust experiences tremendous pressure. To maintain balance, nearby blocks of rock are forced upward. Imagine if every time a giant sinkhole opened somewhere on Earth, a massive mountain suddenly rose beside it. It sounds impossible, yet that appears to be exactly what happens on Io. Whenever one region collapses, its weight and the stresses within the crust push neighboring rock upward. Over millions and billions of years, this repeating process has shaped the moon's remarkable landscape. On one side, lava lakes are created. On the other, immense solitary mountains slowly rise from the surface. Io is a moon that is constantly tearing itself apart while rebuilding itself at the very same time. A world locked in an endless cycle with no true beginning and no final end. And behind every eruption, every mountain, every lava lake, and every fracture, there is always the same invisible force: Jupiter's gravity, a relentless gravitational tug that never stops, never rests. Every second it stretches Io's rocky interior, and every second it allows that tension to relax again. One complete cycle every 1.5 days, billions upon billions of cycles over the age of the solar system. But there is a quiet and deeply fascinating truth that scientists are gradually beginning to understand. Io will not remain this way forever. Volcanic activity is a one-way journey. With every eruption, Io throws part of its interior into space. Every cloud of sulfur that escapes is material permanently lost from the moon. Some of that material forms a giant ring around Jupiter known as the Io Plasma Torus. Some of it eventually settles onto other moons. Some of it drifts away into space forever. At the same time, Io's orbit is slowly changing. Its eccentricity, the slight variation in its distance from Jupiter, is gradually decreasing. A time will eventually come when its orbit becomes much more circular. When that happens, the constant stretching and squeezing caused by Jupiter's gravity will begin to fade. Without that tidal flexing, Io's internal source of heat will slowly disappear. One by one, its volcanoes will fall silent. The isolated pockets of magma will cool and harden into solid rock. Those hundreds of volcanoes, with their landscapes of yellow, white, green, and deep red, will eventually become still. The towering solitary mountains will remain, but they will stand in complete silence. Over immense stretches of time, Io will begin to resemble our own moon. A cold, quiet world whose surface is marked by countless craters. A place where almost nothing changes. A place that gives no hint that it was once the most volcanically active world anywhere in the solar system. Io is a world whose fiery chapter will someday come to an end. But that end lies billions of years in the future. What we are witnessing today is only a single moment in an unimaginably long story. A brief snapshot captured while Io is passing through the most energetic, most violent chapter of its existence. In a way, we are incredibly fortunate to be able to observe it now. Had we arrived 100 million years later, we might never have realized that near Jupiter there once existed a moon whose solid surface rose and fell by nearly 100 meters every 1.5 days. A moon whose largest lava lake renewed itself every 475 days. A moon that launched sulfur plumes more than 330 kilometers into space. A moon where enormous mountains seemed to burst straight out of the ground. Instead, we might have looked at it as nothing more than another frozen, lifeless world, much as people believed before 1979. On the morning of March 9th, 1979, Linda Morabito noticed nothing more than a faint crescent-shaped cloud. She could not have known that she was looking at the first evidence of the most volcanically active world in our solar system. She could not have known that a navigation photograph, taken only to verify the position of a spacecraft, would reveal a discovery that would forever change our understanding of planetary science. And she certainly could not have imagined that 45 years later, one of the biggest ideas about that same moon, the existence of a global magma ocean, would itself be overturned by new evidence. That is the quiet beauty of science. It is never truly finished. Every explanation is only the best understanding we have for now. Every conclusion remains open to new discoveries, and every new discovery has the power to reshape everything we thought we knew. As this journey comes to a close, let your thoughts drift for a moment to that distant world, endlessly circling Jupiter in the darkness, a place of fire surrounded by unimaginable cold. A moon that continues its ancient rhythm, stretching, relaxing, erupting, and changing, one silent cycle after another, far beyond the reach of human hands. And somewhere out there, while the rest of the solar system moves quietly through space, Io continues its timeless dance, carrying on a story that began billions of years ago and will continue for billions more. Until then, it remains one of the most extraordinary worlds we have ever discovered.